Hi, thank you very much for listening to my talk. I will talk now about finding all global minimum cuts in practice. My name is Alexander Noe, and this is joint work with Monika Henzinger, Christian Schulz, and Darren Strash. So first, let's look at the problem. What is a global minimum cut in a graph? So we have given an undirected, potentially edge-weighted graph, G, where we have a vertex set V, an edge set E, and potentially we have edge weights C. And we want to find a cut S that partitions the set of the vertices in S and the rest of the vertices. The weight of the cut hereby is the for all edges that go over the cut. So where one side is on in S and the other side is not in S, the sum of the edge weights that cross this cut. And the goal of our algorithm is to find all global minimum cuts. In the bottom example, we have a graph with unweighted edges, so each edge weight is 1, and we can see two cuts of size 2, and these are the global minimum cuts. One of those, the left one, is a so-called trivial minimum cut. So one side of the minimum cut only has a single vertex, and on the right, we have a non-trivial minimum cut where each side has multiple vertices. And we denote the minimum cut weight as lambda, and the best cut we have found so far over the course of an algorithm as lambda hat. In the beginning of an algorithm, the lambda hat is the minimum vertex degree because there's always the trivial cut that separates this one vertex from the rest of all the vertices. So why do we care about the problem? In social networks, we often have clusters of, for example, friends or colleagues, and we can find those because there's no small cut in one of those clusters. Also, if we want to partition a network, a social network, usually the small cuts are a very good way to partition them and not have too many connected people in different groups. Also in VLSI design, a similar idea that we want to separate the different parts of a processor there where there are not too many connections, so we don't have too many long pathways in our VLSI design. In network security, imagine a large computer network such as the internet. We want to make sure that this network doesn't get disconnected. And a small cut is a spot where the chance of disconnection is particularly high because a lower amount of edges have to fail for the network to be disconnected. So we want to know where there are the smallest cuts in the network so we can augment the minimum cut there. Also, it's a very basic problem, so it's often a sub-problem in different more elaborate algorithms. So we want to find a fast algorithm that is able to find the all minimum cuts in a graph very quickly, even for large graphs that have a lot of minimum cuts. So we store those minimum cuts in a so-called cactus graph, where a cactus graph is a graph where each edge is part of up to one cycle. So it's not quite a tree. So there are allowed to be cycles, but each edge can only be part of up to one cycle. And we use this as a data structure to store all the minimum cuts of a graph G. If you imagine a large cycle graph, so we have one cycle, and each edge has the same weight. This cut has a n squared minimum cuts. So we take any two edges of the cycle, and this is a minimum cut. So there are n squared O of n squared minimum cuts. But this the cactus graph only has up to O of n nodes and edges. And a minimum cut is then represented by either two cycle edges or one edge that is not on the cycle. On the left, we see a graph with 16 vertices and 4 minimum cuts, and we can contract all the edges that are not part of any minimum cut and get our cactus graph, where each minimum cut is represented by either two edges of this top cycle of this triangle up top, or the one edge down bottom that has a weight of 2. So there are these 4 cuts of minimum weight. And so we can take either two out of these three triangle edges and have a minimum cut as seen on the left, or we can take the bottom edge of weight 2, and then those are all the minimum cuts in this graph. There are many theoretical algorithms to solve this problem. One of them, which our algorithm is based on, is the algorithm of Nagamochi, Nakao, and Ibaraki, which is a recursive algorithm. I'm just going to give the most basic rundown of the algorithm now. If you're more deeply interested in the algorithm and why it works and how it works in detail, I suggest you best read the original papers. It's a recursive algorithm, and it's able to find all minimum cuts in O of nm plus n squared log n plus n star m log n, where n star is the value is the number of nodes in the cactus graph. So it's more or less quadratic runtime. And the idea is that we first compute the value of the minimum cut, so we know lambda, and then we take an arbitrary edge e and compute the connectivity of this edge and see whether it's part of a minimum cut. If the connectivity is higher than lambda, no minimum cut contains this edge, so we can just contract it. And if the connectivity is lambda, we can find all minimum cuts that contain this edge and recurse on each of these. We compute them all by computing the connected components on the residual graph. And here we have an example. We have this edge E that is part of two minimum cuts. So there are three vertex sets: V1 left of the first cut, V2 in between the two cuts, and V3 right of the right cut. And for each of these vertex sets, we create a subproblem that we recurse on, where we contract everything except for the for this vertex set. So for V1, there's just a single vertex. We contract the whole rest of the graph into a single vertex, so that's a very small problem. For V2, we contract everything except for V2 into a single vertex, and for V3, we do the same. And after we recursively solve the problem on these three subproblems and then combine them. For how this is done in detail, you best read the original papers where this is described in detail. I'm just giving the basic idea. The edge selection is kind of important for the practical performance. In theory, it doesn't matter. The worst case running time is the same, independent from which edge is selected. But if we select an edge that has multiple large components in the residual graph, so we get multiple large problems, the subproblems become smaller much quicker. So we have two examples. On the left, it's how it's supposed to not be. So here we have a minimum cut edge where one of the subproblems is tiny and the other one contains almost the whole graph. And so we get a huge recursion depth because in each recursion step we only can shrink the graph by a tiny amount. And also the problems remain huge, and the flow problem that we need to solve on these problems to compute the connectivity still takes a lot of time. And on the right, this is how it would be a lot better. Is we have a minimum cut that separates the graph into two roughly equally sized parts. So each of the subproblems is only half as big. So we have a logarithmic recursion depth, and also problems shrink much faster. We have a few heuristic strategies to find such a central edge. One idea is that we pick an edge between high degree vertices. If you think of a social network person that has a high degree, is someone with a lot of friends, so they are probably rather central in the network. So we want to find a high degree vertex, the highest degree neighbor of that vertex, and just pick that edge. If that's a minimum cut edge, we can recurse pretty quick. This is potentially a rather central edge, and we can get our problem size smaller quite quickly. Another idea is to find two vertices with high distance. So we compute a BFS from a random vertex, pick the last vertex we found, run another BFS from that vertex, pick the last vertex we found. So the two vertices that were the last ones in the BFSs have a very high distance to each other. And in the shortest path between them, we pick the central edge. And this is hopefully also an edge that is rather central to the network. Now, before we run this algorithm, so we can contract all the edges that have a connectivity of larger than lambda, because they are not part of any cut of size lambda, so not part of any minimum cut. There an algorithm for the single minimum cut problem that wants to find any minimum cut. The algorithm of Nagamochi, Ono, and Ibaraki has a subroutine that is able to compute the lower bound for all edge connectivities in almost linear time, in quasi-linear time. And the conceptual idea of the algorithm is that they partition the set of edges into maximal edge disjoint spanning forests. So in the bottom, we see an example. We have the first spanning tree in red. Then we have another spanning tree in blue. And for each of the green edges, we know that this edge is not part of was not picked for the red and not for the blue spanning forest. So the vertices already have a path between them in each of those spanning forests. So the connectivity is at least 3. So they are not in the first 2 spanning forests. So we have lambda is 2 in this graph. And for the 2 green edges, we know that their connectivity is at least 3 because in green they are connected, in blue they are connected, in red they are connected as well. So we can contract the green edges and continue from there. Other ideas to contract edges that we know are not part of any minimum cut is that if we find an edge that is heavier than our lambda head, our best minimum cut found so far, we can contract that. Also, different idea is if for a vertex one edge is heavier than all the other neighbors, then we know that each cut that would contain this edge can also instead contain all the other neighbors of this vertex and would be a better minimum cut. So there cannot be any minimum cut that contains this edge. There are a few of those reductions that have been used for algorithms for the single minimum cut algorithms for quite some time, and we adapted them to find all minimum cuts. So we make sure that we don't only so usually you had to make sure that at least one minimum cut remains, and we additionally also make sure that no minimum cut at all can be contracted. So also the no trivial cuts. For a vertex that only has a single neighbor, we know that the only cut that contains that edge that is in any form can even be minimal is the one that is the trivial minimum cut that separates this one vertex from the rest of the graph. If this has a vertex lambda head, we remember this trivial cut because we might actually have to reinsert that afterwards, and we contract the edge because we know that this is not part of any other minimum cuts. In order to get good performance, we contract the edges that we find to contract in bulk, and we use a shared memory parallel hash table to do that, so that we also scale to large instances. Now let's look at degree 2 vertices. On the top left, we see a vertex V that has 2 edges, two different neighbors, and there are 4 possible cases. So either the degree of this vertex is lambda or bigger than lambda, so it is a minimum cut edge or not. And also there's the case that both edges have the same weight or the edges have different weights. Now on the top left, we have the edge has a weight. The edge E1 is lighter than edge E2 without loss of generality. And so we know that this edge V2 cannot be part of any minimum cut because V1 and V2 need to have a connectivity at least lambda minus the weight of E1. Otherwise, there would be a smaller cut between V1 and V and V2. And so this edge cannot be part of any minimum cut. So we can contract it. If the same is true, but the V actually has minimum weight equal to lambda, we remember the trivial cut, and afterwards, when we uncontract, we will reinsert that trivial cut between V1 and V and V1 and V2. If the edges both have the same weight and the degree of V is bigger than lambda, there is no possible contraction, so we don't we cannot contract anything. And in the last case, the edges have equal weight, and the vertex weight is equal to lambda. We contract one of the edges at random. We store the trivial cut, and afterwards, when we're out of the recursion, we check whether vertex v1 and v2 were contracted into the same vertex. If they were not, there is a minimum cut between them. So we recreate edge e1, e2 as well, and then have a triangle between v1 and v2. Otherwise, if they are contracted, we can just introduce the trivial cut between v1 and v2 and v, because that trivial cut definitely exists because the degree of v is equal to lambda. So the trivial cut, minimum cut, definitely exists. So we run all of these reductions to improve the performance of the algorithm of Nagamochi, Nakao, and Ibaraki. And now we have the minimum cut characters. And what we can do with that is that we can find the most balanced minimum cut in a linear time. And note that this is not the most balanced. So this is not this does not solve the problem of finding the cut that is the sorry. This is not the NP-hard problem of finding the cut that maximizes the product of the weight on the lighter side divided by the cut weight. It is just out of all the minimum cuts, this is the one that is the most balanced. The balance of a cut is the sum of node weights on the lighter side. And there's the trivial algorithm that has n star cubed runtime, where we just enumerate all n squared cuts and we check the balance for each. And our algorithm to find the most balanced minimum cut does a depth first search starting from an arbitrary vertex v0, which is the vertex on the top right. And for a leaf, this leaf here, the balance of the cut with that leaf is the minimum of the of all the vertices, the weight of all the vertices that are in sum of vertices that are in here, and all the vertices that are not in here, so on the rest of the graph. For a subcactus rooted in VT, the weight of the right block here is the number of vertices that are in VT, plus for all its children, for all its subcacti, the weight of those vertices. And in a cycle, we examine the cuts in the cycle when we leave it in the BFS. So we have computed all the sub cacti, so we know the weights of all these vertices in the cycle, and we try to find the most balanced cut that contains two of the cycle edges. For how we do it exactly, it's best if you look at the paper or ask me in the question time. Okay, now let's come to the experiments. Our algorithm is implemented in modern C++ in C++ 17, compiled with GCC 8 using full optimization. We do parallel contraction and also check for the contractible edges in parallel using OpenMP. Our machine has 16 cores, is an Intel Xeon, and 256 gigabytes of RAM. And we use different graphs from Dymax challenges and also from the SuitSparse matrix collection. It's social graphs, web graphs, co-purchase matrices, cooperation networks, all different graphs. And the graphs have up to 18 million nodes, 261 million edges, and up to 2.5 million nodes in the cactus. And the problem about social networks is that there are always cuts of size 1. So what we did to get a more diverse instance set, there are also cuts of size 0, but we took the largest connected components. And there we compute the all minimum cuts of size 1 and take the biggest block in the center that does not contain any cuts of size 1. So we have a large graph that only contains cuts with a minimum weight 2, and we continue that to get instances that have a higher cut value as well. So we have a more diverse instance set. So first, let's look at the experiments about the edge selection, where we have 4 different variants. One that just picks a random edge. 2 that pick an edge. So this is the edge selection in the algorithm of Nagamochi, Nakao, and Ibaraki. 2 that pick an edge between heavy vertices. One uses the weight of the vertices. So between vertices with high degree, and one includes the edge degree, and one picks the one that just has the biggest neighborhood, and a central picks a central edge. And we can see that heavy weighted and central always perform roughly equal, with central always being a little bit slower, because computing those BFSs, of course, takes time. Random is on some instance it's the best, because it doesn't do anything to select it, just picks a random edge, which is very fast. So if there's no benefit in picking any edge over another one, then it's the fastest. But on some graphs it has a slowdown factor of more than 3.5. So here we have one instance where all the best variants took about 200 seconds, but random took more than 700 seconds. And heavy is the only variant that's never more than 30% slower than the fastest. So in the other experiments we will pick heavy. So we pick an edge between the vertex with the largest neighborhood, and in that neighborhood we pick the vertex that has the largest neighborhood in there. Now we, for the small instances up to 450,000 vertices, we compare the different optimization variants to the basic algorithm of Nagamochi, Nakao, and Ibaraki. If the basic algorithm timed out, so we have a timeout of 30 minutes in here, then we compute the speed up to these 30 minutes. So the speed ups could even be higher, but the algorithm didn't finish for some of those problems. And we can see that on many graphs we have up to 4 orders of magnitude speed up. What does a lot is first contracting all the connectivity, all the high connectivity edges, because that makes sure that we don't have to solve as many flow problems. And also, what also does a lot is that if we just very simply contract the degree 1 vertices, in the basic algorithm, that is always a flow problem that needs to be solved, but we can just in constant time just contract it. Also, the degree 2 vertices are useful in almost all the instances that do not have a minimum cut size of 1, because even if in the beginning there are not many degree 2 vertices, we shrink the graph by performing edge contractions. So at some point, many vertices do have a degree 2, and in many cases for degree 2 vertex we can contract any of those edges, so we get very quick operations to be able to shrink the graph very quickly and continuously do that. So this gives us a large speed up. On the large instances, we compared it to the variant that does do the connectivity checks. And even there, we still get up to, on some instances, we get more than 3 orders of magnitude speed up. And on many, also more than a factor of 100. And all of these experiments were sequential. And in parallel, we ran the full algorithm on 3 huge social networks, Friendster, Twitter, and UK 2007. They have all more than 1 billion edges, and they have up to 14 million vertices in the cactus graph, so a very large set of minimum cuts. And on the right, you can see the sequential runtimes that are up to 20 minutes. And in parallel, we get a speed up of 6 to 9 times using 16 threads on those huge instances. So let's conclude. We are able to find all minimum cuts in large undirected graphs in a reasonable time. And we do this by combining different kernelization routines with an engineered recursive algorithm. And our algorithm is shared memory parallel, so all the parts that can be parallelized are shared memory parallel. And we're able to find all minimum cuts in networks with up to multiple billions of edges and millions of minimum cuts in just a few minutes. What is important future work, what we are also currently working on, is that we want to build a fully dynamic minimum cut algorithm that uses this all minimum cut algorithm as a subroutine. Because if we dynamic graph is a graph that changes, where we introduce new edges and delete edges, and if we introduce a new edge, this does invalidate some of the minimum cuts. They are not minimal anymore. But if we know about all minimum cuts, we are able to still uphold the value of the minimum cut. So this is an important subroutine for a dynamic minimum cut algorithm. Thank you very much for your attention. If you have any questions, feel free to send me an email or ping me on GitHub. Or if you hear this before the ESA question session, feel free to go there and ask me questions. And if this algorithm is of any use to you, feel free to use it. It's in using the MIT license. And I would be very happy if you let me know if you use it, because it's always great to hear if people actually need this. So this would be great. Thank you very much. Yeah, thank you.